Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young. Chapter 1, Theorems of Alignment and the Principle of Duality. Section 11, the Principle of Duality.
It is in order to exhibit the theorem of duality as clearly as possible that we have introduced the symmetrical, if not always elegant terminology. A point is on a line is on a point. A point is on a plane is on a point. A line is on a plane is on a line. A point is on a three space is on a point. A line is on a three space is on a line. A plane is on a three space is on a plane.
The theorem in question rests on the following observation. If any one of the preceding assumptions, theorems, or corollaries is expressed by means of this on terminology, then a new proposition is formed by simply interchanging the words point and plane. Then this new proposition will be valid, i.e., will be a logical consequence of the assumptions A and E. We give below on the left a complete list of the assumptions thus far made expressed in the on terminology, and have placed on the right, opposite each, the corresponding propositions obtained by interchanging the words point and plane together with the reference to the place where the latter proposition occurs in the preceding sections. On the left, assumptions A1 and A2. If A and B are distinct points, there is one and only one line on A and B. Now the same on the right-hand side. Theorem 9, Corollary 1. If alpha and beta are distinct planes, there is one and only one line on alpha and beta. Assumption A3. If A, B, and C are points not all on the same line, and D and E, with D not equal to E, are points such that B, C, and D are on a line and C, A, E are on a line, then there is a point F such that A, B, F are on a line and also D, E, F are on a line. Theorem 9, Corollary 4. If alpha, beta, and gamma are planes not all on the same line, and mu and nu, with mu not equal to nu, are planes such that beta, gamma, and mu are on a line and gamma, alpha, nu are on a line, then there is a plane lambda such that alpha, beta, lambda are on a line and mu, nu, lambda are on a line. Assumptions E0. There are at least 3 points on every line. Corollary 2 from page 25. There are at least 3 planes on every line. Assumption E1. There exists at least one line. Assumption E1. There exists at least one line. Assumption E2. All points are not on the same line. Corollary 3 from page 25. All planes are not on the same line. Assumption E3. All points are not on the same plane. Corollary 4 from page 25. All planes are not on the same point. Assumption E3 prime. If S3 is a 3 space, every point is on S3. Corollary 5 from page 25. If S3 is a 3 space, every plane is on S3. In all these propositions, it is to be noted that a line is a class of points whose properties are determined by the assumptions, while a plane is a class of points specified by a definition. This definition in the on language is given below on the left, together with a definition obtained from it by the interchange of point and plane. 2 statements in this relation to one another are referred to as space duals of one another. On the left, if P, Q, and R are points not on the same line, and L is a line on Q and R, the class S2 of all points such that every point of S2 is on a line with P and some point on L is called the plane determined by P and L. On the right, if lambda, mu, and nu are planes not on the same line and L is a line on mu and nu, the class B2 of all planes such that every plane of B2 is on a line with lambda and some plane on L is called the bundle determined by lambda and L. Now, it is evident that since lambda, mu, nu, and L all pass through the same point O, the bundle determined by lambda and L is simply the class of all planes on the point O. In like manner, it is evident that the dual of the definition of a three-space is simply the definition of the class of all planes on a three-space. Moreover, dual to the class of all planes on a line, we have the class of all points on a line, i.e. the line itself, and conversely. With the aid of these observations, we are now ready to establish the so-called principle of duality. Theorem 11. The theorem of duality for a space of three dimensions. Any proposition deducible from the assumptions A and E concerning points, lines, and planes of a three-space remains valid if stated in the on terminology when the words point and plane are interchanged. Assumptions A and E. Proof. Any proposition deducible from assumptions A and E is obtained from the assumptions given above on the left by a certain sequence of formal logical inferences. Clearly, the same sequence of logical inferences may be applied to the corresponding propositions given above on the right. They will, of course, refer to the class of all planes on a line when the original argument refers to the class of all points on a line, i.e. to a line and to a bundle of planes when the original argument refers to a plane. The steps of the original argument lead to a conclusion necessarily stated in terms of some or all of the 12 types of on statements enumerated at the beginning of this section. The derived argument leads in the same way to a conclusion which, whenever the original states that a point P is on a line L, says that a plane pi prime is one of the class of planes on a line L prime, i.e. that pi prime is on L prime, or which, whenever the original argument states that a plane pi is on a point P, says that a bundle of planes on a point P prime contains the plane pi prime, i.e. that P prime is on pi prime. Applying similar considerations to each of the 12 types of on statements in succession, we see that to each statement in the conclusion arrived at by the original argument corresponds a statement arrived at by the derived argument in which the words point and plane in the original statement have been simply interchanged. Any proposition obtained in accordance with the principle of duality just proved is called the space dual of the original proposition. The point and the plane are said to be dual elements. The line is self-dual. We may derive from the above similar theorems on duality in a plane and at a point. For consider a plane pi and a point P not on pi, together with all the lines joining P with every point of pi. Then to every point of pi will correspond a line through P, and to every line of pi will correspond a plane through P. Hence, every proposition concerning the points and lines of pi is also valid for the corresponding lines and planes through P. The space dual of the latter proposition is a new proposition concerning lines and points on a plane, which could have been obtained directly by interchanging the words point and line in the original proposition, supposing the latter to be expressed in the on language. This gives Theorem 12, the theorem of duality in a plane. Any proposition deducible from assumptions A and E concerning the points and lines of a plane remain valid if stated in the on terminology when the words point and line are interchanged, assumptions A and E. The space dual of this theorem then gives Theorem 13, the theorem of duality at a point. Any proposition deducible from assumptions A and E concerning the planes and lines through a point remain valid if stated in the on terminology when the words plane and line are interchanged, assumptions A and E. The principle of duality was first stated explicitly by Gergon in 1826, but was led up to by the writings of Poncelet and others during the first quarter of the 19th century. It should be noted that this principle was for several years after the publication the subject of much discussion and often acrimonious dispute, and the treatment of this principle in many standard texts is far from convincing. The method of formal inference from explicitly stated assumptions makes the theorem appear almost self-evident. This may well be regarded as one of the important advantages of this method. It is highly desirable that the reader gain proficiency in forming the duals of given propositions. It is therefore suggested as an exercise that he state the duals of each of the theorems and corollaries in this chapter. He should in this case state both the original and the dual proposition in the ordinary terminology, in order to gain facility in dualizing propositions without first stating them in the often cumbersome on language. It is also desirable that he dualize several of the proofs by writing out in order the duals of each proposition used in the proofs in question. Exercise. Prove the theorem of duality for a space of 4 dimensions. Any proposition derivable from the assumptions of alignment and extension and closure for a space of 4 dimensions concerning points, lines, planes, and 3 spaces remains valid when stated in the on terminology, if the words point and 3 space and the words line and plane are interchanged. Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.